In this video, I will try and simplify the loss function. Hello all budding data scientists and machine learning engineers. My name is Neeraj Sabnani and welcome to Artificial Intelligence and Machine Learning Simplified. In this video, we will cover the meaning of loss, error, cost, typically used in the training of neural networks. We will also understand different types of losses for classification and regression. So during the training process, at the end of each epoch, a loss is computed. And loss is computed by comparing the actual output and the predicted output. And during this training process, we try and minimize this loss by continuously adjusting the weight such that by the end of the training, this whole loss is minimized. We use these different terms like loss function, error function, cost function. So typically, loss and error terms are used interchangeably. And when we consider one training example, we call it as a loss or the error. However, when we consider the entire training data set, or in cases of mini batch gradient descent, we consider a mini batch, then the loss associated with this data is called the cost function. So having understood loss and the cost function, now let's understand the common types of loss functions used for regression and classification. So for regression, some of the common types of loss functions which are used are mean square loss, mean absolute loss or error or Hubbell loss. Similarly, in case of classification, some of the commonly used loss functions are binary cross entropy, categorical cross entropy, KL divergence, and Hinge loss, specifically in the case of SVM. Now, let's consider an example of regression where we want to predict the price of the house using multiple variables like size of the house, number of rooms, age of the house, location of the house, etc. We compare the predicted value, that is y hat, with the actual price of the house and compute the difference, which we call it as loss. And then we take the square of that and also divide by half so that it becomes easier from the differentiation perspective. So now let's understand the loss visually. Let's consider a data set with two variables and where we can easily fit a regression line through that. So as we fit the regression line, during this process, we compute the error and we do the subtraction of this y hat, which is a predicted value, with the y. Then we take a square of it and we call it as a square loss or square error. And when we take the average of this whole data set over the entire data set, we call it as mean square error or MSE in short. The form of equation here is a square or a quadratic equation, and the advantage is it is easily differentiable, which is required for finding the gradient descent as part of the training process. Another advantage in this is the local minima is also the global minima for this quadratic function. So when we optimize the cost function and find the point of minima, this point will be also the point of absolute minima. So as we apply the training and during the training process, as we try and fit the regression line through this data set, we compute loss at each step. And as part of the training or the optimization process, the objective is to reduce this loss value through different iterations, and learning continues till the time we are able to minimize this loss and we are able to reach to the point of global minima. And during this process, the weights of the network keep on changing as part of the learning, and this all will continue till we are able to go to the point of global minima as shown in the graph here. And also at this point, if we see, we will also get the line of best fit. So in case there are some outliers which have been added to the data sets, let's see what happens? This regression line will try and accommodate these outliers as well. And the regression line or the regression model will change accordingly. Since the loss here is a square of distance from the regression line, these outliers will have a bigger impact because of the square part of it, square of the distance, because they have a higher distance. And then the line of best fit, which was a line which was here, will move, or the regression line will move or will adjust to accommodate these outliers. And also the error function will become unstable. So to reduce this problem of high influence by some of the outliers, we look at another error function which we call it as absolute loss or absolute error. In this case, we look at the difference between the predicted y value, that is y hat, and then y, and then we compute the absolute value for this difference. And when we consider the whole data set, we get something called mean absolute error or MAE, as was the case with MSE. So the challenge with this absolute loss function is that gradient is not defined at a zero value. However, we also have an advantage with respect to the outliers. That is, the outliers will be treated in the same way as any other point in the data set. And let's say if these outliers are not very important and can be discarded, we will get a line of the best fit which will cover the rest of the points. So considering the challenges from both these types of error, we come up with a modified loss and we call it as Huber loss, which uses both of the loss functions, that is mean square error as well as the mean absolute error. In this case, for low values of delta, delta is another hyperparameter which has been added in the Huber loss. For the low values of the delta, that is in the region around 0, the loss will be same as square loss. Whereas in the regions which are away from 0, it will be using the absolute loss and then it will multiply with delta and minus half of delta square. So it is able to leverage both the losses and able to combine and get the benefits of both the losses. So having looked at the regression losses, now let's try and understand the losses associated with the classification. So in the classification model, we have class as an output. And the probabilities we get from the model are called the predicted probabilities. And we compare it with the actual probability or the actual value. And the comparison of these two values gives us a loss function. And this loss function is known as cross entropy. But before we understand cross entropy, let's understand the concept of entropy. So entropy was derived from an information theory paper given by Shannon in 1948. It considers how uncertainty is reduced when a message is communicated from a provider to the recipient and how this message reduces the uncertainty for the recipient and provide the information to the recipient. So let's say consider a scenario if we have a data set having two classes with equal probability of 50% each. That is, each class can occur with equal probability. And there is a high amount of uncertainty associated with this data set because both the classes are present in equal proportion. And whenever we pick up a record, it can belong to any of the two classes. Hence, if we have a model that is able to segregate one of the classes, we will be able to reduce the uncertainty by a factor of half, that is by 1 bit. Similarly, if there are 8 classes with equal probability and model gives an output corresponding to one of the classes, then we will be able to reduce the uncertainty by a factor of 1 by 8 or 3 bits. And we leverage the same concept in AIML. So the formula for entropy is minus P log Pi, which is summed over for all the classes. We take the minus to make the overall value as positive. Now let's look at the cross entropy. For an AI/ML model, the model predicts the probability, and let's say predicted distribution is Q, and we have the actual distribution as P. So the cross entropy, which measures the loss, that is the difference between the two probability distribution P and Q, where P is the actual and Q is the predicted. And we have a formula of Pi log Qi summed over all classes, and again taking the minus to make it positive. Now, for the binary classification, we call it as binary cross entropy. We have we look at the formula where the probability of the two classes will be y hat and 1 minus y hat corresponding to the value of prediction or the q, and we can replace the earlier formula with y and y hat values where p would be corresponding to y and y hat will correspond to q. We can extend the same to multiple classes as well, where for multiple classes the formula will become yij log of y hat ij for all I and j values. So let's understand a little bit more about cross entropy computation for multi-class with the help of an example. Let's say we pick up an example of a digit recognition. So in this example, the input to the neural network is digit 5, and we get the probabilities for different numbers as an output. So these are the output classes between 0 and 9. And the predicted probability in this case is for digit 3, we are getting a probability of 0.1. For digit 5, we get a probability of 0.8. For digit 6, 0.2. And for digit 8, we get a probability of 0.1. However, the actual probability is there only for one of the class, that is digit 5. It will be 1, and then it will be 0 for the rest of the classes. When we apply the formula for categorical cross entropy, only corresponding to class 5, e will have a value of 1, and for rest of the terms it will become 0, and accordingly we will have only one term in categorical cross entropy minus log of 0.8. So having looked at cross entropy, let's look at the another form of loss function called KL divergence. So as we know, as we have seen the different forms of entropy and cross entropy formula, since we are trying to predict the probability, if the predicted probability distribution is same as the actual probability distribution, the cross entropy in this formula will become same as the entropy. Whereas in the cases where probability distributions are different and cross entropy is greater than the actual entropy, we call KL divergence as cross entropy minus actual entropy, HPQ minus HP. So our objective is always to minimize this KL divergence for such that we are able to reduce the loss. Another form of loss used in classification is Hinge loss, and this is commonly used in SVM, specifically in the case of binary classification. And the objective is to maximize this margin. If there are points which are falling in this margin in the classification or during the test phase, there is a penalty associated with them, even though classification is correct. So just to recap, we covered multiple losses. We covered the loss function, we covered the error function, and we indicated how they are associated with the cost function. Then we covered different types of losses for regression, like mean square loss, mean absolute loss, Huber loss, and then different types of losses for classification, binary cross entropy, categorical cross entropy, KL divergence, Hinge loss. There are additional losses as well, but I covered few of them which are more commonly used. I hope you found this video useful. Please like this video by clicking on the like button and share with your friends. Kindly subscribe to the channel and to receive the new updates. Thank you all and happy learning.